First of all, before we start, the first thing to check is the datasheet. I have opened the PM 2008 datasheet, and here you can see the I2C section. In the case of I2C, there are mainly two ways to use it. One is to send a command, and then, for now, we will ignore the command and just check the reading of the values that are read. We will only check the read data command at this moment. In order to proceed, we will send the command and subsequently check the data that is read. The first part corresponds to the address, and it states that a total of 32 bytes are read. However, I clearly explained last time that for the PM 2008, the address is 0x28 in hexadecimal. Here it shows 51 and for sending commands. There are cases where the corresponding address is 50. The reason why each datasheet has different explanations like this is that when you convert the hexadecimal 0x50 to binary, it just looks like this. But right now, the binary is like this, and if you cut off the last digit from this binary, it becomes 28. The reason the I2C address is 7 bits is that when viewed in terms of 1 byte, only the first 7 bits actually correspond to the address, while the last bit is used to distinguish between writing and reading, which is why 7 bits are used. So, as stated in the datasheet, if you write a value, when I write values to an I2C slave, such as an electronic component, sensor, or even a liquid, I attach a 0 after the address, indicating a write operation. If I am reading a value, I attach a 1 instead, indicating a read operation. In this case, with a 1 attached, it becomes 51. And for the command earlier, with a 0 attached, it becomes 50. So, in hexadecimal, it is 50. However, the commands can vary slightly depending on the specific hardware platform. In the case of Arduino, it automatically appends 0 or 1 when reading or writing. So we only need to know the actual address when looking at data sheets. The address is indicated in the first part as being based on the I2C standard, specifically stating that the address is 7 bits, such as, so it is 0x28, but here it is indicated as 0x50 and 0x51, which is different. You just need to understand that this is the reason for the difference. Next, as we saw when discussing the protocol format is also established here. It's a bit different from what we did, and it varies among different sensor manufacturers. So you just need to send and receive data according to the rules here. In this case, the value corresponding to STX is 0 to 16, and the value corresponding to the land is indicated to come in as 1 byte. In reality, the data bytes range from P3 to P31, and in this case, there is currently no ETX. And finally, the checksum. The checksum is the same as what we did before. We will perform an XOR operation from the first byte to the previous byte. Let's write some code to retrieve this ourselves. First, since we need to use the R-squash rival now, it would be good to include the shop, include wire and blow, and then declare the macro constants for the address and STX in advance. So I will define the address as 0x28 and define STX as 0x16. Next, you should allocate the necessary buffer space in advance. This step is crucial to ensure that the subsequent processes can proceed smoothly without any interruptions. Once the buffer is allocated, you can then move on to the next step in the procedure. Now, I will add the code for initializing the wire next. After begin, you should definitely call serial begin 9600 and wait until the serial connection is established, just like you always do. Additionally, when it comes to serial communication and controlling GPIO or hardware, it's better to place the hardware control code before the serial code. So, it's best to complete all the hardware-related settings first and then attempt to establish serial communication. In order, you will do it this way, in a step-by-step manner, and then, approximately every 3 seconds, you will read the sensor values from the previously established protocol. At this particular point in time, a completely separate and distinct function or method will be specifically created to handle the process of reading. Next, in the specific and detailed case of reading, it is a wire request originating from the specific address of 32 in the context of a wire request. In the case of a request, since it involves reading, as I mentioned earlier, you shift 1 bit to the back and add a 1 at the end to make it a hex. Value of 51, just like before. Here, when using Arduino, you can simply use the request from or any commands related to write, and you only need to input the actual 7-bit related address. And now we need to know the exact buffer position in detail. So this particular part of the wire is almost exactly the same as when we did serial communication before, which involved similar steps and procedures and processes to ensure accuracy. So, the wire is, in essence, basically similar to the TB wire in serial communication, right? While inserting, increase it at the corresponding position. Next, if IDX buffer is 32, it exits. This is the code format, so it automatically adjusts the format, but when the lines are crooked, it's good to write it out once in a while. If the IDS buffer is 32, since 32 repeats in this case, I will just write it essentially arbitrarily. 32. And this can keep accumulating in the buffer until it reaches 32, at which point it may break and come out. But there could also be cases where it becomes false before reaching 32 bytes, causing it to exit. In that case, since the data would be insufficient, it is considered invalid, which is why this function is designed to terminate. I don't have time to show it visually right now, but ideally it would be good to have the error displayed here. And now, we need to check the STX, which stands for start of text, then check the CS, which is the checksum, and then if buffer 0, STX, if the first byte is not, SDX, which stands for start delimiter, then it terminates. After that, here TCS is buffer 0, and TI is 0, so from here it's now. Rand -2, -1. To elaborate, the STX is a control character used to mark the beginning of a text block, and the CS is used to verify the integrity of the data. If the first byte in buffer 0 is not SDX, the process will terminate immediately to prevent errors. The TCS, or temporary checksum, is set to buffer 0, and TI, or temporary index, is initialized to 0. From this point, the calculation involves subtracting 2 from a random value, and then subtracting 1 from the result. 32, 31, 30, 31, that's up to 31. Random. Subtraction 31, so CS is the operation with X, buffer, I. In this case, the last bit will become 31. So the XOR operation will continue for I up to 30, a maximum of 30. So if this is different from C_lambda1, then we need to consider the implications and understand why this discrepancy exists in the first place. Let's return to our main task. Here, I've carefully performed the checksum operation, which is crucial for ensuring data integrity. If this operation succeeds, the system will display an OK message, indicating that everything is functioning correctly. Now let's go ahead and run the program to see the result. It definitely says OK, clearly. Now, as shown in the datasheet, after successfully parsing, we initialize the wire and serial and call the read function every 3 seconds. Here, we request to read 32 bytes, and then the wire continues to loop infinitely while the data is valid until the buffer fills up to a length of 30. If it fills up or becomes invalid, it exits. After that, if the ID buffer is shorter than the expected length, it indicates a failure, and we exit. We also check the checksum, and if it fails, we exit. Up to this point, we have succeeded. Once successful, as indicated in the datasheet, you can continue parsing the data byte by byte. I will skip the details related to parsing. This part can be skipped because you just need to look at the datasheet and retrieve the corresponding bytes in order to display them. In this session, we explored reading the sensor data of the PM2008 using I2C. Of course, for most well-known I2C sensors or actuators, there are Arduino libraries available. However, there may be cases where you have to perform I2C communication directly, or even on other platforms that are not Arduino. That's why I showed you how to communicate in this way. In a way, it's similar to UART communication. And the key point to remember is that you need to check the datasheet carefully. Communicating is not that difficult, but when you look at the datasheet, you may find that each sensor has a different protocol and different checksum methods, and these can vary slightly. So if you can resolve those parts, you will probably be able to perform I2C communication directly without any rivals. Then I will see you next time.